I'm going to get this thing going and we're going to start. Okay, so it's funny, I say we're going to start and then you guys start talking. Like, start talking. Put your phone away! Are you looking at Ninja Brian? Yeah. Okay. Ninja Brian. I told you. Did I lie?
It's a real person.
It's a real person.
Is there a picture with him next to the couch?
I didn't get to put that in before I got in trouble.
All right. Okay. Are there any physics questions from residual things from last time that we can talk about? Because today we're basically going to spend our time filling in that missing piece of the golden rule, the m squared thing. So. Okay, yeah.
So for scattering events, we said we can use things like conservation of charge to see what's possible.
Yeah. If that'll help you like cut out. So you could just put all possibilities and then calculate them, and a lot of them will end up being zero, the probabilities. And you could have figured that out before doing a calculation by using arguments like conservation of charge and kinematic constraints and things like that.
So for something like color charge?
Yeah, color charge, and we'll talk about, when we talk about doing these calculations and strong interactions, we'll see how color charge.
So quarks would scatter off of each other?
Yeah. So but we'll see that in time when we come to QCD. Mark?
So usually when I've seen Bernoulli's golden rule, it's only like a first order approximation to like the perturbation theory.
Sure.
Is there ever any reason why you have to go out to second order with the iron particle physics?
Well, so it's first order in this well, we're going to go to higher order in the dynamics. I don't. Maybe if you were doing extremely low energy scattering, you would have to go to higher orders in the kinematics, but I'm not sure. I'm not 100% sure. We'll definitely look at how you go to any order in the dynamics.
Okay.
But with the kinematics, I'm not 100% sure. So I have to think about that. Questions? I did modify your homework slightly this morning, if you've looked at it. The second problem, I'm actually going to work out some of that today. So I actually changed the second problem into a slightly different and more interesting problem, and then moved it to the end. So the first and last problems were the same as they were originally, and then the lifetime of the A and the ABC theory, I'm going to have you do that slightly differently. Okay, so what we're going to talk about today are the Feynman rules. And again, the Feynman rules are essentially going to give us that quantity m, which appears in various places in the golden rule, and of course we find it with its complex magnitude squared, but we're going to learn how to calculate m itself. And we're going to start by doing this in a toy model, something called the ABC theory. And the reason we're going to do this is because there's just certain ideas and sort of little steps that you need to kind of get familiar with before we tackle the subtleties that come in when you actually deal with things that have spin or are represented by matrices, and you got to worry about commutation. So at the ABC theory, everything's going to be scalars. You don't have to worry about the order of stuff. You can write things in any order without worrying about it. And you guaranteed that if you just multiply everything together, you have a number. You don't have to worry about combining things in a certain way to make a number. Okay, so we'll spend today talking about the ABC theory, and we might possibly be able to move on to Spinner's next Tuesday. But here we go. The Lagrangian of the ABC theory is as follows, and I'm going to write it like this. I'm going to do sum over I, 1/2 d mu phi I d mu phi I minus 1/2. This is in brackets mic over h bar squared phi I squared. And then we'll have this one little term at the end, minus g phi A, phi B, phi C. And here the sum goes over A, B, C. So basically, can anybody identify this term right here in brackets? That's the Klein-Gordon kinetic term. It's the free Klein-Gordon Lagrangian. which we should expect since we're dealing with scalar particles. The Klein-Gordon is good for scalar particles. Now this might be realistic if you were maybe talking about the interaction of the Higgs boson with itself, but we're not trying to make a realistic application of this. I'm just using this as a toy example to get you familiar with the Feynman rules. And then we'll actually see how you apply this to something like QED and strong interactions in the coming weeks, okay? So, does this theory have an interaction?
Yes.
Yes, it does. How do you know it has an interaction? Yeah, there's an extra term. We have the free term, but then there's this guy, and it's a product of different fields, which we've mentioned several times, usually indicates some kind of an interaction. Okay, so a couple of things to point out about this just before going forward. We have 3 real scalar fields. Okay, the phi's in here are real. We don't have to worry about any complex conjugation like we had to do with the Higgs boson. Since they're real, they are actually their own antiparticles. So we can say A bar equals A, etc. So there's no need to distinguish between particles and antiparticles. And this following bit is a constraint I'm going to place on this theory. Okay, so it doesn't come out of what I've written. It's just a condition that I'm going to deposit, and that is that the mass of particle A, or field A, if you will, is larger than the sum of the masses of B and C. Now that's going to be important because eventually when we consider processes, we have to take into account kinematic constraints. Is this thing big enough to decay into this, et cetera, et cetera. So we have to know something about their relative sizes. Okay, again, that doesn't follow from this Lagrangian. This is just something I have to state, but it's something I'm going to work with. And then last but not least, and this is perhaps the most important thing, is based on this Lagrangian and the form of the interaction, the fundamental interaction of this theory I can represent by a diagram that looks like this. Now I want to talk a little bit about this because this is actually one of the key components in building Feynman diagrams. Whenever we have an interaction, well, actually, let me back up. The fact that we have a kinetic term for a field means that a line for A, a line for B, and a line for C they all make sense and they're well defined. These particles can exist and they can propagate. Okay? If I did not have this term, this is all my theory would allow, just freely propagating states. However, owing to this interaction term, when particle-like excitations of A, B, and C get near each other, they can have an interaction. There's a locality principle underlying this. And I represent that in the Feynman diagrams by what we call a vertex. And here, this vertex has to include all 3 of these. Okay? It can include more. I can't do this, because this would require a quartic term in the Lagrangian. I can't do 2 of them, because that would require a quadratic term, but we already know that would have a funny interpretation anyway. It would just say that A spontaneously turns into B, which is telling us something is weird. So what I have at my disposal in drawing pictures are these lines and these vertices. Now I can take this thing and I can rotate it as I want. I mean, I don't have to, I can have it like this. I can have A here, B here, and C here. None of that matters. Now in the past, when I've hinted at these Feynman diagrams, and I've drawn a few to illustrate some examples, I've often drawn a little arrow on some of the lines. Those arrows were actually there to indicate whether the particle we're dealing with was a particle or its antiparticle, which we have to worry about if we have like electrons or neutrinos or any quarks. But since this theory is just particles that are their own antiparticles, there's no reason to put these arrows on the lines. Okay, so I won't be drawing any arrows. If you're wondering where are the arrows that you've been putting, we will revisit the arrows next week when we start bringing in spinners. Okay? Are there any questions about this? Yes, Alex.
How is it arbitrary in which orientation you place them? Because doesn't time move to the right?
That's exactly true. So in all of the, and I'm about to start drawing diagrams, and I would have added in that element. So time, when we draw these diagrams, is going to be understood as flowing to the right. So the far left is what you initially start with, the far right is what comes out, and then whatever's in between is kind of what's connecting the beginning and the end. Okay, so you're right. It's not. If I rotate it, I'm changing effectively what's happening. But there's nothing that forbids me from rotating it, I guess is what I'm saying. I'm just saying that the fact that this is written as phi A, phi B, phi C doesn't dictate that the only picture you can ever draw is this.
Okay. They are different, it's just any is allowable.
Right, exactly. Good. Okay. Other questions? Marky.
If you rotated it though such that like A and C were coming in, like that bottom one, wouldn't that not conserve mass?
Sure. Yeah, we haven't even gotten to actually building processes and asking whether they're allowed or not.
Okay.
And that's what we're about to get into. Okay. All right. So what I'm going to do now is I'm going to actually start going through a particular process just to give you an idea of how we come up with the diagrams that contribute. So this example is actually, it was originally the homework problem that I then changed. It's still, the homework problem that I created is very similar to this, so the ideas I'm about to throw out to you are still going to be useful for your homework problem. So what we're going to do is we're going to consider the lifetime of A. Or if you will, the decay of A. So what can A decay into? So when you think of a process like this, and maybe I should say this. I should probably add in a bunch of conditions so that you don't have extra crap to worry about. Actually, those aren't something you need to worry about. If we have A initially, so again, time flows to the right, so I start out with an A, and then that A is going to decay. Now, A cannot decay into A, that doesn't make any sense, not really decaying, okay? So for A to decay, perhaps we could have a B and an A come out. Jacob, why is that not allowed?
Because then the mass isn't conserved.
Because the mass is,
Not conserved.
say it again?
Isn't conserved.
Well, mass is, well, let's not say that mass is conserved, because mass doesn't have to be conserved in special relativity.
The mass going out is greater than the mass.
Yeah, the mass going out is bigger than the mass going in, and that's one of the things we learned as a stopping point for considering decays. The mass of what comes out has to be less than what goes in, okay? So this could be a B.
Yeah. Kind of.
All right.
If A was moving really fast, it could have.
And it turns out that if you actually try to connect this guy with these outcoming particles, you can't. There's no combination of these vertices that will allow you to start with an A and come out with two Bs. You can sit and play around with little combinations all you want, and it won't happen. Okay? Similarly, if you made both of these Cs, okay, you wouldn't be able to put together a combination that does this. So the obvious candidate here is A goes into B plus C. Okay? Now you could postulate other things. You could maybe have A go into two B's and two C's, but these mass constraints are telling you that now you have too much mass coming out based on what went in. Okay? So for now, it looks like that in this theory at least, A can only decay into a B plus C, and you notice that I have been very hesitant to fill in the missing pieces. Okay, yeah.
I apologize. I missed why we couldn't go into just two Bs or just two Cs.
Because if you actually tried to connect an A into two Bs using these vertices, you would not be able to do it. You can play around with combinations and see if you can get it to work, but you won't.
Based on that same argument.
No, no, no. This is based on just building pictures out of this. These are exercises you should definitely try. I don't have time to sit and go through every possible combination of these vertices, but it's the kind of thing you should play around with a few times to get familiar with. Oh, I'm not saying it's obvious that that's the result. I'm telling you that's the result, and you can verify it on your own. It takes just some plugging, drawing pictures and seeing if you can make it work. Okay? Now, how do I connect? So this is my initial state over here. This is the A particle, and then this is my final state, the B plus C. How do I connect them? Okay, now is where the aspect of these Feynman calculations, that this is a perturbative calculation, comes into play. We start drawing every possible connection between the incoming and the outgoing particles, every possible way of connecting them, starting with the simplest, and then working our way up to more and more complicated pictures. Okay? So for example, does anybody want to take a stab at what the simplest possible picture would be? I know, it's pretty straightforward. It's just A goes into B plus C. Okay? And you might say to yourself, what else are you going to do? Well, I could have A go into B plus C, where at this vertex, I create a C and a B, and I have an A. Now stare at that for a moment. This is important. Notice, every vertex in this picture has an A, B, and a C. A, B, C. A, B, C. They're all built out of that fundamental vertex. I could not just arbitrarily come in here and make this a C, because that would involve a vertex that has B, C, C, and B, C, C, which is not part of my theory. Okay? But there you go. I have managed to draw a slightly more complicated diagram, still built out of this fundamental vertex. Jacob?
Does that need to be the same A going into the the bottom triangle like vertices? Could you have two different A's going into there, or?
Sorry, into here?
Yeah. So like, could you have one A going into there, and then like, and you have the A connecting both B and C there? Could you have
This one?
No. That one. So from that one to the one above it, you have just one A.
Yeah.
Could you have two separate A's going
No,
into?
no. It's a line is a particle.
Okay.
So if you ignored the vertices, that's just a line describing the free propagation of a particle A.
Yeah, but like,
Maybe you should come up here and point to what you're trying to say, because
so like, if you got rid of this line, could you have another line coming in here and another line coming in here?
oh yeah, okay, yeah, good. So what about this? So maybe this is an A and this is an A. Okay. What's the problem with that?
These are A's. Those are initial A's.
Yeah, where are those A's coming from? Because these lines have to come from somewhere, so they would have had to be part of the initial state.
Okay.
I'm only allowed to work with the initial state and the final state that I specified. So that diagram makes sense, but it's not part of this process. This
Okay.
process has one A to start with and nothing else, and it has a B and a C at the end and nothing else.
Okay. I see.
And you now see the advantage of working with this A here, because it begins and ends within the diagram itself. It doesn't have any sort of external existence. Now, of course, you're probably all aware that if we were going to give these particular funny little particles names, since they only exist sort of within the diagram, they do not correspond to any physically external observable states, these are what we call virtual particles. Okay, so these are virtual particles. When I use that word, I'm referring to particle lines which begin and end within a given diagram. They do not correspond to external states. Now, is that the only? Now, let me ask you this question. Could I draw another diagram with just 3 vertices?
Rotate it.
Can I rotate it?
Oh, no, because of the mass constraints.
No.
Yeah, can I rotate this?
A little bit.
Yeah. Well, if I flip it vertically, okay, that's a really interesting question, which we'll address a little bit later on in doing calculations. But when you do vertical flips of things, what are you really changing? And that's actually a very, very important and somewhat subtle question. So let me hold that off till we actually calculate something for this. Okay, you guys, that's it for 3 vertices?
Oh,
Dude, I could draw 3 more. Actually, I think I could draw.
You could keep drawing triangles attached to these vertices.
How about
It's not 3 versus the trigger.
oh my gosh.
A, B, C, A, B, C?
That's more than 3 vertices.
It is? I see 3 vertices. 1, 2, 3. Or how about A? I heard people say this is awful.
Well, you never told us we could bend our line.
Yes, you didn't tell us this is a chemistry class.
Look, I'm not expecting you to be comfortable with this. That's why we're doing this with a toy theory where we don't have to worry about all the other crap, okay? Now, observe. I drew 3 more pictures, and they all have 3 vertices. They're all built out of this vertex. Okay? The good news is that's it. That's all I can draw at the level of 3 vertices. I can, of course, draw more, higher order or higher number of vertex diagrams. Okay? Now, you might say to yourself, well, is there a limit to how many I can draw, first of all? No. I can clearly draw an infinite number of diagrams with just ever-increasing complexity. So you might say to yourself, what is the point of this? This is stupid. You draw an infinite number of pictures, how are you going to do a calculation with it?
Integrate.
Well, I'm going to go ahead and I'm going to skip to a punchline, which is what kind of underlies the utility of all of this. And that is the following. When these diagrams they're pictures, but they're really just useful guides for calculating M. At the end of the day, I'm going to do a calculation of a number. And here's the very, very, very important observation. When I calculate M, and we're going to lay down some rules for how you do the calculation of M, but I'm going to go ahead and skip to this one. When I calculate M for a diagram, for every vertex, there is a factor of G, the coupling. That, of course, means that in these diagrams, the coupling comes in at G cubed. And for higher order diagrams, you're going to have factors of higher than G cubed. And the important observation is, if G is less than 1, then I can get hopefully a very good approximation to the answer just by writing down the first 2 simplest diagrams and calculating those. Okay? So this idea of some series expansion in a small parameter and making an approximation by keeping the first 2 terms, you've seen this hopefully several times in your math and physics classes by now. And this is the same idea that underlies perturbative dynamics. That is, the interaction G, if it's weak, if the coupling is small enough, then the more and more complicated the interactions, the less and less significant they are. because the interaction is weak. It is much less likely that this will provide a strong contribution to a calculation compared to something simple. Yeah?
So are we forcing this number that we calculate to converge or not? Because, so is G less than 1 a restriction that we want for physical systems?
Okay, so that is a very interesting question. We can set up this formalism of doing calculations, but then the question is when we apply it to physical theories, those theories have a coupling. And the question is the coupling less than 1? And just to skip to the end of the semester, for electricity and magnetism, the coupling is less than 1. For the weak interactions, the coupling is less than 1. For the strong interactions, at low energy, the coupling is less than 1. And at high energy, is that right? The energy flow, the coupling. So at low energies, the coupling is larger than 1. And at high energies, the coupling is less than 1. So for the strong interactions, you can't use this kind of analysis at low energies, only at high energies. And you might say, wait, energies, why does the coupling depend on energies? Again, this is a story that we're going to see play out for the rest of the semester, that these things we've called constants, like masses and couplings, those are actually going to be functions of energy through renormalization. That's something we'll develop.
Is that kind of why the nucleus is stable at lower energies? Is because the strong interactions get the...
Because the what?
Because the strong interaction has a high coupling?
Why the nucleus is stable?
Yeah. Or nucleoids.
No. I'm sure it has some role to play in the stability of the nucleus. I can't directly. So when we actually draw diagrams for QCD, you're going to realize that nuclear interactions at the nucleon level is a very, very complicated thing. We like to think it's just, oh, they're just exchanging a gluon. It's way more complicated than that. And you'll realize that when you just try and draw the simplest diagram. So I can't take that complex story and extract the very simple statement that that is the reason the nucleus is stable. It's a little bit more detailed than that. Okay. So for our purposes, we're rarely ever going to go beyond, say, third order. Okay? I mean, maybe on the final, if I'm in a bad mood when I write it, I'll ask you to go to 10th order. But you can see the problem is it's not just that the diagrams get a little bit more complicated, but they proliferate. There were 4 diagrams at third order where there was only 1 at first order. And you can imagine if you go to the next highest order that you get more than 4 diagrams. Yeah.
Is there a way to know how many diagrams there are at a certain order, given the type of interaction?
Yes. Well, there are ways that you can argue that there's only odd order diagrams, based on a certain configuration of interactions, but I don't think there's just an overarching rule. It's a combinatoric problem. A lot of people have fun playing around with the combinatorics of Feynman diagrams. This interaction in particular is a rather simple one that we don't actually encounter this particular type of interaction too often actually no, we do in the weak interactions. We have 3 different particles meeting in a vertex. But like for QED, it's 2 of the same particle and then a third. So there's no blanket answer for all the interactions. It's case by case. All right, so these third order diagrams, actually, they can sort of be organized into sort of useful modifications of this picture. We call this particular diagram a vertex correction, because if you will, it kind of takes this fundamental vertex and it just kind of blows it up into something that's a little bit more complicated than just a point. Okay, so this is a vertex correction, and we can have higher order vertex corrections. So this diagram itself could have a correction at each vertex of this form. These are somewhat different. I mean, you probably noticed that this is really just a bubble that appears in an A line. here a bubble in a B line, and here a bubble in a C line. Okay? Those kind of diagrams we call self-energy corrections. Because they genuinely, I mean, forget about this process, they genuinely are diagrams that you would have to consider if you just had an A going along and it just decided to burp out a B and a C that then annihilate and come back together and form an A. Okay? And rather often as you start, especially when you go to higher order and you get many, many, many of these diagrams, it's often useful to arrange them into what exactly are they providing higher order corrections to? Are they vertex factor corrections, are they self-energy corrections, etc. This will also be a very useful organizational tool when we talk about renormalization, because what we'll find in renormalization is that higher order corrections to vertex factors change the effective value of the coupling, whereas higher order contributions to the self-energy of particles corresponds to modifying their effective masses. But that's a story that we'll see somewhat at the end of the semester. Okay, so again, it's just kind of like Tinker Toys. At this point, we could almost teach this to third graders, but the next part we can't teach to third graders. And that's how do you calculate with these things. All I've done so far is drawn pictures. I haven't showed you how to get a number out of it. So let me go through now what are technically called the Feynman rules. Where am I going to do this? Actually, here is what I'll do. I will go through the Feynman rules, and as I walk through the Feynman rules, I will work out a particular diagram. So let's start with this diagram, A, B, C. Okay, that's the leading order diagram in the decay of A into B plus C. And by the way, there was another piece of nomenclature which you might encounter. I might say it, and you might encounter in the literature, but you'll notice this is the only diagram that doesn't have a loop. Whereas all those other diagrams I drew, they have kind of an internal loop. This is often called a tree level diagram, and these are loop corrections. So the tree level of the leading order diagram, we're going to calculate the factor or the contribution to M from this diagram. Each and every diagram gives us a contribution to M, and we add them all together. Okay. So the contribution to M from this diagram I construct as follows. So first, we're going to, I'm not going to write it in words, I'm just going to do it in the picture. So the first thing we're going to do is we're going to label all of the momenta in the diagram, where if we have an external momentum, we label it with a P. If we had an internal line, we would label its momentum with a Q. Now remember, time flows to the right, so I should think about these particles as kind of moving to the right, as being motion forward in time. So I wouldn't want to make my momentum arrow to the left. And then I can assign momenta to particles B and C. Okay, we're going to do a loop diagram next, and you'll see where the complications of internal lines come from. So the next step is for every vertex in our diagram, we write down a factor of minus IG. Now, all of the rules that I'm giving you essentially follow from the Lagrangian. I'm not going to talk about how you get them from the Lagrangian today. We'll talk about that next week, all right? But what you write down for a given vertex is actually information that you strip out of the Lagrangian. For this particular theory, it's almost so simple, what else could you write? It's got to be G, maybe times some constant. For other interactions, it'll actually be a little bit more complicated, but we'll read it off the Lagrangian. So for every vertex, I write down a factor of minus IG. And then If we had internal lines, which we don't, we would write down propagator factors for those internal lines. And again, when we do an example with an internal line in a minute, you'll see how to write down a propagator. Those internal propagators will have undetermined momentum that we then integrate over, but again, we're not going to have to worry about that for this particular. I don't know why I'm taking this simple diagram. I'm just going to do the more complicated diagram. This is stupid. Sorry. I'm going to do the vertex correction. All right, here we go. What goes here? Good. All right, here we go. P1. I'm going to call that P2. I'm going to call that P3. Now I got to label the momenta for the internal particles. All right? To distinguish internal from external particles, I'm going to call the momenta for the internal particles Q. And what's interesting about the internal particles is it does not matter what direction you draw the arrows. Because to be truthful, there's no real interpretation of time in terms of what's going on with virtual states. For example, what the hell does a vertical line mean? Well, it doesn't matter. We would never draw a vertical external line, but for internal lines, you just don't have to worry about the interpretation. So I'm going to just pick some, I'm going to make it go clockwise. What the hell? So I'm going to say this is Q. Let me actually grab my calculation so I can be consistent with what I wrote on my notes. I'm going to call this Q4. Maybe I'll do it out here. So I'm going to call this Q5. And I'm going to call up here Q6. Now, again, I'm not drawing arrows on the lines themselves. These momentum arrows I draw next to the lines. Drawing arrows on lines of the diagram is, again, referencing whether it's a particle or an antiparticle. That is completely independent of specifying the momentum. So I've labeled everything on my diagram. Now what I want to do is, again, for every vertex, write down a factor of minus ig. How many vertices do I have? 3. Okay. So I'm going to have a minus ig cubed. Okay. Now, since now we have internal lines, 3 of them, for each internal line, I'm going to write down a factor which corresponds to what we call a propagator. Okay? And the form of a propagator is essentially, in this theory, and it's different in different theories, I over the momentum of the particle squared, so I have Q4, minus the mass of that particle squared c squared. So this is a c particle, so this would be the mass of c squared c squared. Okay. That factor is, for this theory, the propagator associated with particle c. And then I write down a similar factor for all of the other internal momenta. Okay, so what am I writing down for Q5?
Q5 squared minus mb squared c squared.
Say it again.
Q5 squared minus mb squared c squared.
And then I over that.
Yeah, I over that. Good. All right, so I over, put that vertex back to back. Q5 squared minus mb squared c squared, and then for the other one I would have Q6 squared minus ma squared c squared, and then my minus ig cubed. Okay? Now I have a question. If Q is the momentum of these particles, and everywhere I write momentum here, it's 4 momentum. If Q is the 4 momentum of, say, this particle here, what's the problem with writing this expression?
Does that go to 0?
Say it again?
Does it go to 0?
Why?
Because P mu is MC squared, or M squared C squared.
Yeah, if you apply the mass shell condition, The mass shell condition says that p squared is equal to m squared c squared. Seems odd. Why are we writing down I over 0?
These are virtual particles, so they don't have to obey the mass shell.
Exactly. Virtual particles do not have to obey the mass shell condition. In a sense, you can trace this back to this whole funny idea in quantum mechanics of uncertainty. If you have something which is taking place over a short enough period of time, you can sort of borrow energy. So these particles don't actually live but for a very brief, tiny period of time, and so their energy is not constrained to its normal value. That's one way to think about it, kind of how some people feel good about it. The bottom line is they're not real particles, and only real particles have to satisfy the mass shell condition. Okay? Now, the next step, which is kind of fun, is at each vertex, we need to make sure that momentum is conserved. After all, conservation of form momentum is one of the sort of underlying kinematic things that should be built into, yeah.
So we can use that with virtual particles?
Conservation of form momentum?
Yes.
Sure.
But we don't use mesh shell.
Yeah, you don't use the mass, well, the mass shell condition doesn't have anything to do with the conservation of form momentum.
Yeah, but I'm just wondering what we apply to virtual particles, like what kind of conservation laws apply?
Well, that's what I'm saying, that you, well, yeah, I guess. So why would you apply conservation of form momentum but not yeah, I kind of understand why you would ask that question. If you don't apply conservation of form momentum, it's going to be almost impossible to understand how you're going to have overall conservation of form momentum from the beginning to the end. So, imposing conservation of form momentum at each little vertex, at the end of the day, it's going to create for us the condition that the overall momentum is conserved. However, allowing internal particles to go off mass shell doesn't have any impact, for example, with the external particles being forced to be on shell. I don't know. I don't know if I want to tie something satisfying the mass shell condition to a conservation principle. I mean, we do say that the square of the form momentum is an invariant, therefore, but
So say we had charged particles, would we imply that the virtual particles have to obey charge conservation?
yes,
So
yeah.
it's more than
So the conserved, yeah, I guess that's the, so mass is not a conserved quantity, we know that, right? At a vertex, mass can change. However, the conserved quantities are form momenta, charge, color charge. Those things are legitimate conserved quantities. They have another current coming from bearing the action, and there's some conservation principle that underlies the statement that they can't change. Mass, however, is not a conserved quantity. Okay, so how are we going to impose momentum conservation at a vertex? How are we going to force the momentum coming in to be equal to the momentum going out? Say it again?
P1 equals P4 plus.
So I'm going to write in here P1 equals Q4 plus Q5.
You're going to do the delta.
Say it again?
Use your delta.
Yeah, you throw in a delta function. Like, that doesn't make any sense. Right? Stick it in. Multiply it by P1 equals Q4 plus Q5. But if I write this, then that delta function says, unless these things cancel, what you're calculating is 0. Okay? Yeah, Rob.
Why is it delta before?
It's a delta function over a 4-component object, a 4-vector. When you distinguish that from delta functions for scalars. Now, when we write our delta functions, you can track. You can go through. Let me see where. Yeah, 2 pi to the 4th. Is it 4 and 5? every time we write a delta function, that bad boy is going to come with a factor of 2 pi to the 4, and I'm not a master at keeping track of 2 pi, so I'm not going to worry about it. It's just every time you write a delta function, throw in a factor of 2 pi over 4. Anytime you do a momentum integral, divide by a factor of 2 pi over 4, or 2 pi to the 4. We'll do that in a minute, but let me go ahead and conserve momentum at the other 2 vertices. So I've conserved momentum at this vertex. What about this vertex? Go ahead and write down what you would use to conserve momentum at this vertex in your notes. When you get done with that, write down what you need to conserve momentum at this vertex in your notes. All of these things are multiplied together. Yeah, Peter.
And so we're going to multiply all of this together, and in the end, this all equals the matrix element.
Why are you asking that? Do you not think I'm going to tell you? That's the weirdest question to ask.
I don't know.
Are you going
it just
to
seems like
read
we're
this?
writing all of this
Yeah,
down.
we're writing all this down,
What the
and
point
at the end of the day, we're going to get a number out of it.
and that
And that's
number-
M. That's the contribution to M from this diagram. And then we have to do it for the next diagram, and the next diagram, and add them all up. And hopefully, if the coupling was less than 1, we can get away with just 2 diagrams. Okay, so you guys have written down the delta functions you need. What delta function do I need to conserve momentum at this vertex?
Q4 plus Q6.
Does it matter?
Q4 plus Q6 minus V2.
That? And what about the other vertex?
Q5 minus Q6.
Everybody agree? So you'll notice if I had flipped the direction of this Q, it would change sign in these delta functions. Okay? So assigning directions to the momenta, even though it's arbitrary for these Qs, it is going to impact what you write down. But the important part is, the next step is to integrate over all of those Qs. So we're not actually fixed to a particular value of Q, like we are with the initial momentum and the outcoming momentum. These values have to match up with the values that you're putting into the golden rule. These Qs are they have to completely disappear when we calculate M because there's no space for them in the golden rule. These are purely internal. So the next step is now, after we've conserved 4 momentum, we integrate over all of the internal 4 momenta with a factor of d4q4 over 2 pi to the 4th, d4q5 over 2 pi to the 4th, d4q6 over 2 pi to the 4th.
You only integrate over the momentum of virtual particles.
Yeah, so at the end of the day, this M should be a function of P1, P2, and P3. Because if you look at the golden rule, that's why you can't pull it out of the integral. Because the golden rule is integrating over P2 and P3. And M, if it's a function of those, which we expect it to be, will have to remain inside of that integral. Okay. Now, I wish I could say that this was M and that was it, but it's not. But that's actually all we have to write down for now. Before we can actually extract M, we have to start evaluating some of these integrals. He's clearly very excited about this class. Is this that boring? You guys I can't believe Thornley's going through a calculation. This is the most boring thing on the face of the planet. Okay. We should all start with
Every time you
That will probably keep the rest of you from falling asleep. Okay, so before I can actually extract what the value of M is, we're going to have to start doing some of these integrals. But most of you probably noticed that I have a bunch of delta functions at my disposal. And in fact, I'm integrating over quantities that appear in these delta functions. So the next step in this kind of calculation is integrate everything you possibly can. Get rid of as many q's as you possibly can. You're not always going to be able to get rid of all of them. Okay? And then after you've gotten rid of as many q's as you can, then we can go to the last step and identify m. So what I'm going to do now is I'm going to use, so now I'm just going to go through some of these integrations. I'm going to use this particular delta function, p1 minus q4 minus q5, to get rid of q4. Okay, so how do I use this delta function to do this integral? What do I do? Henry.
It says Q4 equal to P1 minus Q5.
Yeah, so the delta function tells you that this integral is 0 unless the argument of the delta function is 0. So this thing has to be equal to 0. So I can just take the value of Q4 that makes this 0, but that is Q4 equals Q5 minus P1. Is that right?
No. Opposite.
Negative.
Yeah, I man, I'm terrible at sine. Thank you. I was trying not to actually reference that song, but that's good. Okay, so if I set Q4 equal to P1 minus Q5, then this delta function is 0. That is the only value of Q4 that actually contributes to the integral. Yeah?
So could we just solve the system of three, or I guess n equation n unknowns, to just substitute that in there, and then we have essentially evaluated the integral?
You have what?
Like with the delta functions, they force Q4, Q5, and Q6. But we will always have as many delta functions as we have variables.
No.
No.
No. That's not necessarily the case.
You always have
So I don't want you to jump to, like, oh, we can. That's not always going to be the case. Okay. So what you're trying to say is that the number of vertices tracks the number of internal lines. And in this case, that's true. I had 3 vertices and I had 3 internal lines, but that's not always the case. And it's going to depend on the details of the particular theory too. Because there are, in the weak interactions, there's vertices with 4 lines. Okay. So yeah, in certain cases you might be able to do that, but I don't want to start making rules that are only useful in certain special cases. Okay. So now that I've done this integral, unfortunately, I have to go back and take what I've written and actually apply the substitution. So my first propagator here is going to become P1 minus Q5 squared minus MC squared C squared. My remaining propagators are as they appear. And please, folks, don't be like Physics 1 students. You have to label masses appropriately. You can't just put M, because these particles have different masses. So MC, MA, B, and C where it appears. I still got my Q6. I still got my I minus IG cubed. And now I've used up this delta function, so this no longer appears, but I still have these 2 delta functions, but I have to rewrite this guy without Q4. So this delta function is going to become 2 pi to the 4th delta 4 P1 minus Q5 plus Q6 minus P2. Still have that delta function remaining. Okay, and then I integrate over D4Q5 and D4Q6.
Are you not canceling the pies just to screw with them?
Yeah, I know, I'm being stupid. I'm being stupid, you're right. You can't just cancel it. Yeah, you're always going to have cancellations in the pies.
Okay. Do we even have to keep track of them? Because it seems like the number.
You don't have to. There are people who like to
Okay.
keep track of them, but yeah.
Yeah.
Okay, now, I don't, this is long, but I hope you see I'm just doing the same, I'm going to do the same thing several times. So if you're lost, I'm not doing anything hard. I haven't asked you to do an inverse hyperbolic trigonometric substitution to evaluate the integral. I'm just plugging things in algebraically using delta functions. It's long and it's tedious. Okay, it's busy work, if you will. Okay, but so far that's all I'm doing. I followed the rules and wrote down this big ass triple integral, and now I'm just banging it out a piece at a time. And you do not have to do it in the particular order that I'm doing it. You could just sub out whatever cues you want. I just happen to have my notes written up doing it in this order. Okay? I'm not done yet, so where we're going is still to be determined.
How do we know this gives us the right answer?
Versus what? I mean, we're told to do an integral and we're doing it.
Sure, but we're gonna end up with this m, right?
Yes.
And then we're gonna put that into the way that we calculate, probabilities.
Sure. No. That's a fair question. So how would you do this? So here, so we're calculating essentially the lifetime of A, and we've got to construct M, and then we're going to put it into the formula for the two-body decay lifetime that we got from the golden rule last time. To calculate M, we've got to draw all the diagrams, and we've got to calculate, in principle, all infinite number of them. But fortunately, if G is less than 1, we can just calculate the lowest order ones, get an approximate value of M, stick it into the golden rule, and doing the integrals in the golden rule with the value of M that we calculated, we will get a number for the lifetime of A. Then we get a whole bunch of A's and we watch them.
Yeah.
We see how long it takes for 1 over E of them to disappear.
And that matches.
And that should match what comes out of this. Now, it would be very difficult to get a whole bunch of A's and do this experiment because this is not the real world. This is the ABC theory. But if you were in Mr. Rogers' whatever neighborhood, maybe you could. Okay, but that's how you would verify that this is the correct procedure. Okay? So, oh my God. All right, proceeding. The next step that I'm going to do, and again, you don't have to do it in this order, but this is just how I have it written up. The next step is I'm going to use the delta function Q5 minus Q6 minus P3 to do the integral over Q6. Okay? So what that, of course, means is that I want to take Q6 and set it equal to Q5 minus P3. Right? Everybody on board? Okay, so erasing all this garbage. So you guys can go ahead and start writing this down. I mean, all you're doing is taking this expression here, and everywhere you see Q6, plugging in Q5 minus P3, right? So while you do that, I'll do it up here. All right, and just to appease Alex, I'll cancel the 2 pies. Thank you.
If you really want to write them up there, it's all your fault for writing them up.
All right, this is cool. When I go to, so now I'm using this. So when I go to this delta function, now watch folks, when I go to this delta function and I plug in the condition on Q6, do you notice something that happens? All the Q's go away. So this delta function, this last delta function, once I've substituted in used all the other Q's from the other delta functions, This last delta function is going to just say P1 minus P2 minus P3. Okay? And then all of that is integrated over D4 Q5.
Is this always going to happen?
Yes.
Vertex?
This is always going to happen. That after you've evaluated all of the delta functions you can possibly evaluate, or sorry, evaluated all the integrals you can evaluate with delta functions, you're always going to be left with an overall delta function which just conserves the external form momentum. And so, Martin, now you see why the conservation of form momentum at the vertices actually eventually guaranteed this, because the delta functions just feed into each other. And at the end of the day, we should have expected this. Okay? Yes?
So is it like an okay-ish rule to say, or a pattern, that you can always just jump to this, kind of like, instead of running?
No, not at all. No. What I can tell you is you can always expect that this will come out, but in getting to this, that's what's going to determine the form of these factors, and that's going to be different in other different calculations. Okay? Now, we are at long last in a position to state what M is.
That's equal to that.
I know. So the last Feynman rule, the very last Feynman rule is the following. Oh, yeah. I do need the 2 pi's for the last Feynman rule. Yeah. So multiply this by 2 pi.
And the point is made that they might not always be the same because you might have different numbers of vertices.
No, you're always going to have, well,
It could be different.
yeah, no, you're
Particles are not the same.
yeah, no, you're right. Okay, so one thing you'll notice is that there is only one undetermined momentum in here, one Q. Okay, so I might as well just call it Q. I don't need to call it Q5 anymore. But this factor doesn't depend on Q, so I can pull it out of the integral. All right? So at the end of the day, once we've evaluated all the integrals that we can with our delta functions, this is the last step of the Feynman rules. Erase this factor. Erase it. Then multiply by I to get M. Okay.
So you don't actually evaluate the
Well, no, so you would evaluate the integral if you could, and in certain situations you can. In this class, in most circumstances, I'm not going to ask you to evaluate that last integral. It would suck.
So M is equal to the integral, not...
The M is equal to this, so I mean, here I'll write it.
Okay.
That's M. When you read your homework assignment and I say that you need to calculate M, but you can have one unevaluated momentum integral left, that's what I'm talking about. Don't try and evaluate that last integral. If you can't do an integral with a delta function in this class, you're not going to do it. Yes?
So just erasing that term, are we doing that because in the other integral where we have everything else, that term's already there?
Yeah, so that is already going to be part of the golden rule, so it's a redundancy to have it in there. Now you might say, why in the world do you multiply by I? Because after all, aren't we going to square it?
Does there always be a odd number of vertices? You go on the negative side.
I mean, what you're going to take the complex magnitude squared. So multiplying by I is, it's not going to change M squared, is it?
So we want to do it.
Huh?
Well, it's probably will change M squared, otherwise you wouldn't do it.
Well, we want to be careful because our M, remember, is the sum of a whole bunch of terms. It's not just one term.
Right, yeah, that's another, multiplying everything by I and then taking the magnitude of that isn't going to keep it the same.
Yeah, because you can factor out an I and then it's magnitude times magnitude.
So why are we multiplying by I?
Well, each,
Because there was a screwed up sign convention.
Because you switched metrics.
Yeah, so the difference is whether you're actually interested in the quantity m, okay, which is if you're doing quantum mechanics, this is actually the transition amplitude between the initial state and the final state. It's the quantity m, and it's a rigorously defined thing. Fortunately for us, we're calculating numbers that we directly carry over to observations, so decay rates, lifetimes, all right? So it's true that the actual numbers that you're going to compare to experiment are not going to be complex numbers. They're going to be real numbers. They're going to depend on m squared. But in the formalism of quantum mechanics, to actually identify what the transition amplitude is, you have to make sure whether you're working with the right quantity or not. It's true that at the end of the day, you square it and the imaginary component of it disappears, all right? So you don't have to write this I down if you're eventually going to square everything and put in the golden rule. But if I ask you to calculate m, which in many cases I will do, just make sure you throw in the I so that you're writing the correct expression. Okay? It's true at the end of the day, you know, it's not gonna, I mean, it's like if I have a wave function and I multiply it by I, do I actually change the probability distribution associated with the wave function? No. But technically I've changed the wave function if I multiply it by I. Okay. All right. So that was a complicated example. Let's actually go back and do an easier example. All right. So let's do this example, A, B, C directly. Okay. There are some very important things that we have to keep in mind when we are calculating different diagrams corresponding to the same process. For instance, I have to use the same external momentum labels here that I used here. So if I call this P1 and I call this P2, I need to make sure I use the same labels in each diagram. The reason for that is because I'm going to add up all of these and then put them into the golden rule, and the golden rule is going to deal with P2 and P1 and P3, and it needs to make sure it's always associating P2 with the same outgoing particle. So I got the same momentum labels that I had up here. There are no internal momentum, so that's not that interesting. So, are you ready? What's the first thing we write down?
IG.
We write down a factor of minus IG, and then what's the next thing that we do?
Multiplied by delta.
Delta function and going on.
So do we have any internal lines to write down propagators for? No. So then what's the next step? We conserve momentum at each vertex using delta functions.
But you're just going to divide by that anyways.
Yeah, and erase it.
And then the next step is we integrate over all internal momenta. There are none. Then we use all of the delta functions that we have at our disposal to evaluate all the integrals, of which there are none. After we've done that, we're done. We erase the overall momentum conserving delta function, multiply the answer times I, and that's M. Okay? So if on an exam you were asked to do the tree level versus the one loop calculation, which one would you do? I would do tree level. Okay. Martin?
So that's always going to be the case that M is equal to the coupling and the tree level diagram. Because we will always have this. We won't.
No, that's not the case.
Well,
it depends. Look, and I understand. Maybe that's what it is. Is there's this kind of interesting combinatoric structure to this, and it's really, and especially when you watch me draw these two pies, and why did you cancel them for? You're such an idiot. And it's really tempting to make these sort of statements, but unfortunately they're overgeneralizations. For example, that is a tree level diagram, but it has an internal momentum. yes, for this particular process, the tree level diagram has no internal momentum, and so it simplifies like that.
So,
But
can you break that into two and call the first part what we have? Yeah.
no, because this diagram has a momentum that gets integrated over. It doesn't have a definite outgoing momentum. I mean, yeah, in a certain sense, this is going to kind of go like this, with one exception being that this guy doesn't have to satisfy the mass shell condition like external momentum do. Okay, so just I want you to be careful about drawing, and if you do calculations in your homework, do them. Don't try and guess the answer. Go through the steps. Okay, so I have now at this point shown you two contributions. Notice order G cubed. If G was a really small number, we could probably just write this and be done. Of course, the form of this momentum integral might give us some interesting effect, and it will turn out to be a very interesting effect. But overall, we see a G cubed dependence, and so we would expect this contribution to M to be smaller than this one. If we do the other three third order diagrams with the bubbles, I'll get expressions very similar to this, except where the Q is and the various propagators will change. It will still end up looking very much like this. One integral over an undetermined momentum and an overall factor of minus IG cubed, because they're all third ordered. But the details of the integral will be different for each diagram. I take them all, add them together, and that would give me so if I take all of these, I call this 1, I call this 2, and I have, what is it, 5? Yeah, 1, 2, 3, 4, 5. And then I plug this into the golden rule for decays. That will give me the lifetime of A to third order in G. So if I say to you, do a calculation to third order, do a calculation to fourth order, what I'm referring to is the order of the coupling, or the number of vertices in the diagrams. You should always compute everything up to that. If you only did the third order ones and you forgot this one, you would be missing a very important part of the answer. Okay? So there's a couple of more examples that I'll post in the notes. I actually do the calculation for one of the bubbles. So I'll post that in the notes. I'm certainly not going to write it up on the board. And then I'm also going to post the calculations associated with scattering events. So if I want to scatter, say, an A and a B into an A and a B, well, that's how I realize that at leading order. However, I could, actually, let me do it this way to make more sense. I could have another leading order diagram.
CBC and CBC vertex?
Yeah.
Can you do that?
Yeah, that's supposed to be an A. So I have two leading order diagrams for this scattering process.
So when you have, so in your simplest diagram, that one you have two vertices. Now whenever you have any addition, are you automatically going to have the same even or odd number of,
It depends on the theory.
Okay.
Okay, and there are certain, like in the ADC theory, you can actually go through and you can do a combinatoric evaluation of for how many external lines, how many internal vertices do you have to have.
Okay.
And it's true for the ADC theory, but it's not necessarily true for something like the weak interaction. So I don't want to get too hung up on that. Peter?
Do the vertices tell us anything about the positional?
No. That you don't read too much into the pictures that you're drawing. Yeah.
For the cube that you're left over with, when
Yeah.
you're solving for M, does it matter which one is actually left over?
It doesn't matter as long as it's an integral over one remaining cube.
How are those two different on the board?
Okay, that's an interesting question. How are these two different? Can anybody tell me? And this is actually a really, really important question. How are these two diagrams different?
C is virtual on the right.
C is virtual in both pictures. Remember, whatever is to the far left is what you start with, and whatever is to the far right is what you end with, and that's the same in both pictures. What's different?
A and B become the virtual C and then split back to A.
Well, what's more important, it's the same, it's included in that statement, but what's important is, in this diagram, the momentum of C has to carry all of the momentum of A and B. However, in this diagram, C carries the momentum lost from A to B. Or, sorry, from A to B here. So if this starts out at 100, and this ends up at 99, the momentum of this is 1. Okay? Whereas if this starts out at 100 and this starts out at 99, the momentum of this is 199 because momentum is conserved. So the momentum of assignments of the internal particles can be very different depending on the diagram. See?
Yo, Henry. No, it's mine. Okay, I don't have my back. I don't want to take it. Finds the box. She's like, why did I never see Henry and Larry? Then she decides to and she walks down and laughing about it. Like, I sent these letters to Steve. He's like, Steve's the ex-convict, the guy that saw things. He loves me. He's saying that you're still in love with him.
Settle it and smash. You played last night? Yeah. Their Wi-Fi broke.
They drive to the hospital in the convertible. He parks. They walk on to the hospital. They're arguing all the way into the hospital. She's like, "I'll talk to you after I'm off work." He's like, "Fine." So he gets in his car. He says, "It's night." She's like, "Night." Oh yeah. There's like flashes of light. It's like he's driving down the highway. And he's like seeing street lamps. And he's on his back seat. And he notices that with the rear view mirror. He's like, "What the hell?" And he keeps seeing it. He's like, "What the shit is this?" And he's freaking out. So he finally slams on his brakes, running over one of the street lights, turns around, and shoots back home.
Right? That's my favorite. I love that joke.
I like that. I know. I'm sorry. I made you feel so. I made it so bad for you. That's great. That's my favorite one. I really like that.